Hello students, your professor Dr. Mink, and welcome to the first audio lecture from your Java Foundations textbook for Computer Science 1, CSC 122. In this chapter, we'll start with an introduction to Java, one of the most popular programming languages used in industry today. We'll talk about how a program is compiled and executed in Java. We'll be using the NetBeans IDE for this class. Problem solving in general and the software development process. But one of the most important topics, which will be carried throughout this entire course, is object-oriented programming principles. This is a slide that I'm sure you've seen before in other introductory courses, or especially the course which is a prerequisite for this course, but we'll leave it in here. Obviously, hardware and software make up a computer, and hardware is the physical, tangible pieces that support the computing environment. A program, which is what we'll focus on in this class and follow-up classes, a series of instructions that are executed by the hardware. And programs are often called applications or apps. Software consists of programs and the data that these programs use. Java was originally created by Sun Microsystems and introduced in 1995. I was in graduate school at that point in time, and I remember almost vividly the first time I was introduced to Java in a class. And so some other details about Java, the Java programming language, which makes it very similar to other languages, is that the language specifies the words and symbols that we can use, also often referred to as the syntax or the grammar of the language. And so Java uses syntax that's very similar to other object-oriented programming languages. And you're going to see, well, many of you have had to take C++ as a prerequisite to this course, and you'll see some very significant similarities. Java is an object-oriented programming language, and the focus of this course is object-oriented programming. We just happen to be using Java. And in Java, a program is made up of one or more classes. You'll see a class is kind of a blueprint. And a class contains one or more methods, and a method contains program statements, similar to a function in C++. Okay, and we're going to drill down on classes, methods, objects in very significant detail. It should be noted that a Java application always or must contain at least a method called main. Here we have a very basic Java application that has a single class, and that class is named Lincoln. And within that class, we have the method main. And if you forget about the access specifiers, public and static, void main looks like a void function from C++. All this function does is print 2 lines of output. Here we're taking a more detailed look at the class myProgram. You'll see it has a class header, and within the braces, it has the body of the class, and within there, we'll have objects and we'll have methods, etc. Comments can be placed almost anywhere and have the same format or begin the same as comments in C++, 2 forward slashes. Anything following that is a comment. And there's other various ways of extending comments, but we'll get to that in a slide or two in this presentation. By now, we all know that documentation in the form of comments is critical to every program you develop. So on this slide, we'll just take a look at the 3 forms that comments can be used in using Java. The first is very similar or exactly the same as C++, 2 forward slashes, and the comment runs to the end of the line, or a forward slash and an asterisk on the at the beginning of the comment, and then an asterisk forward slash to end the comment. And the third is an asterisk, forward slash followed by 2 asterisks, which creates what's called a Java doc comment. Java doc is a utility used with the JDK to automatically generate documentation for the program, and it also allows use of HTML hashtag statements. And I'll put a link to an explanation of Java doc from the documentation I have in this week's timeline session. Java's rules for identifiers are very similar to the rules for C++. Identifiers can include letters, digits, the underscore, and the $sign. I'm trying to remember. I don't think you can use a $sign in an identifier in C++. And as with C++, the identifier can contain digits, numeric digits, but it cannot begin with a digit. And Java is case sensitive, and by convention, programmers and us being students and teacher will use different case styles for different types of identifiers. So we will use a title case for class names, and we'll use uppercase for constants. Sometimes we create or choose the names of identifiers when writing a program. And sometimes we're using another programmer's code, so we have to use the identifiers that that programmer chose. An example would be print line. And sometimes we use special identifiers that are reserve words that already have predefined meaning in the language. And a reserve word cannot be used in any other way. You cannot reuse a reserve word. The slide contains a list of Java reserve words that have to be used exactly as stated on this slide, and that cannot be redefined or reused in any other way. As in most other high-level programming languages, especially C++, prerequisite for this course, spaces, blank lines, and tabs are called white space, and white space is ignored, typically used just to separate components of our program, segments of code. A valid Java program can be formatted in many different ways, especially because Java, the compiler, will skip or ignore white space. But we should always write our programs so that they're formatted in a way that makes them easy to read. You shouldn't use different indentation formats or standards within your particular program. And what I'm getting at is most of us will develop a style, and it needs to be readable, and it needs to be easy to debug and troubleshoot by people who weren't the original authors of the program. So here we have an example of a Java application, a program that's poorly formatted, really poorly formatted. However, it is totally valid. And there's no separation between the class we have on the same line as the class declaration, the beginning of the main method, and then its body has very little white space separating the program statements. And then the end of the class statement and the end of the main method are on the same line. It's just really hard to read. However, this is totally valid code. I have another example coming up next. So in our previous example, we used very little white space. And here we are at the other end of the spectrum where this is a valid program, but it is, once again, poorly formatted because there's no consistency. And you certainly wouldn't want white space separating the declaration of the public class, Lincoln 3, on two different lines. And it's just, I mean, it is valid, but it is just very difficult to read. Once again, the content of this slide should be nothing new to you. The mechanics of developing a program. You write the program in a specific language, such as Java. One unique aspect of Java is that it's architecture neutral programming language, which we'll get to in a few minutes actually. And you translate the program to a form that the computer can execute. And then obviously you're debugging, fixing various types of errors that occur. And there's software tools that will be used all along the way to help with this process. There are 4 programming language levels, and we'll discuss them from machine language, which is first generation. That is the abstraction level 0. That is the actual code that runs through the processor. And each machine language is specific to the CPU and the instruction set architecture. For those of you in the computer science program, which should be everyone in this class, currently I'm the only professor teaching CSC 240 computer organization, and we're going to learn a lot more about machine language, which is first generation language. Assembly languages, second generation languages, are one level of abstraction away from machine language. It is considered a low-level programming language. And it has some aspects of a programming language that machine language doesn't, such as labels and mnemonics, etc. A high-level language, also referred to as a third-generation programming language, is the universe of almost all programming languages that you'll use within this program. And then fourth generation language are closer to human language than any other high-level languages and are accessible to people without formal training as programmers. They allow multiple operations to be performed with a single programmer-entered command. They're intended to be easier for users than any of the other languages, but there is limited access to or limited availability of fourth generation languages. In this slide, we'll see an expression in a higher level language, the sum of A plus B, and then how it is expressed in its lower level language equivalents. Assembly, so the higher level language would be a third generation language, and then the assembly language is a first generation programming language, abstraction level 1 away from the CPU. And you'll see mnemonics, load, you'll see floating point, etc. And then the machine language to generate A plus B is shown on the right. And that looks like a 16-bit instruction set architecture. Next, we discuss the process of compilation, obviously done by a compiler. And a specific CPU executes only a particular machine language, and it's called the CPU has an instruction set architecture, and that is the universe of instructions that CPU can execute, and the microarchitecture designed to support that instruction set. So a program, a high-level program, must be translated into a machine language targeted for a specific CPU. And so a compiler does most of the heavy lifting. Excuse me. It's a software tool which translates the source code in a specific high-level programming language into a specific target language. Now, this is almost always the case. Unfortunately, or fortunately, it's not how Java works. All too often, the target language is the machine language for a particular CPU type. The Java approach is somewhat different in that it is architecture neutral and involves an extra step, which we'll get to next. So a programmer writes a program using an editor, and it's then compiled into an executable form and then executed by the processor. This is the typical scenario. You know, if errors occur during compilation, an executable version is not created, and those errors are typically syntactical in nature. There are other errors such as runtime and logic errors that we've all learned about in prerequisite courses. So next we move on to the Java translation process, which involves a compiler and an interpreter. The Java compiler does not translate Java source code into machine language. It translates it into a special representation called bytecode, Java bytecode. Java bytecode is not specific to a CPU. So then another software tool called an interpreter is used to translate the bytecode into a specific instruction set architecture's machine language and execute it. So the Java compiler is not tied to any particular machine, okay? Thus, Java is considered to be architecture neutral. Here we see a graphical depiction of the process I just described. So the Java bytecode is not, which is the output of the compiler, is not specific to a CPU. Okay, it's not ready to run on a 32-bit Intel processor or 64-bit Intel processor or a whatever. Then the targeted machine code is generated by the interpreter, which is really a bytecode compiler. In this course, we're going to be using the NetBeans IDE. IDE stands for Integrated Development Environment. Development environment has a set of tools for creating, testing, debugging, modifying a program, and it's all combined into one software program. And all development environments contain a compiler and an interpreter. Other Java IDEs include Eclipse, a very popular one, a couple others that are not as popular. So, as I mentioned earlier, we're going to be using the NetBeans IDE, and that's just a set of tools used to write, test, debug, compile, interpret our code. As I just previously mentioned, there are other development environments, including Eclipse. The JDK you have to install the Java development kit in order to use NetBeans. So that's kind of a prerequisite, if you will. BlueJ and JGrass I've not used. I've used Eclipse and NetBeans. Although these environments look a little differently, the basic compilation and execution is essentially the same. The topics on this slide should be review, but worth repeating. The syntax is the grammar of a language, and it defines how we can put together symbols, reserved words, identifiers to make a valid statement, which in turn becomes a series of statements that makes a valid program. The semantics of a program statement define what that statement means or its purpose. However, a syntactically correct program or program statement is not necessarily logically correct or semantically correct. A program will only do what we tell it to do, not what we meant to tell it to do. And so, logic errors are often some of the most difficult to resolve, whereas a syntactic error is typically caught by either a smart editor in the IDE or the first run of the compiler on the code. Once again, this is an introduction to the course, and we are covering some topics that are absolutely prerequisite to this course, but we'll go over them real quickly. 3 types of errors. A compiler or a smart editor will find syntax and other basic problems, which are referred to as compile time errors. Runtime errors are typically program errors that are encountered as a result of input that's not been validated, such as a divide by zero error. And a program may run but produce results that look correct but are incorrect. Perhaps there was a calculation error with an incorrect formula used, or there was a logic error. So these are often very difficult to track down because the results, maybe from a formatting standpoint, and maybe even from an output standpoint, look correct. But that's one of the reasons we're going to use test data, proven set of inputs, or proven set of outputs from a given set of inputs. We write programs to solve a problem, generate a solution to a problem. And solving a problem involves multiple steps, which are not purely linear. Some of these are iterative. But first, you need to understand the problem. And then you need to design a solution to the problem. And during that process, you need to consider alternatives. And often an alternative will be identified, and you're back to understanding the problem, designing a solution. And only until after those 3 steps, which are somewhat linear, but also iterative, because they'll stop, you'll identify a problem and go back a step, and it can be quite iterative. Only after those 3 steps are fully played out do you implement the solution in a programming language. And sometimes, even after implementing the solution, you'll have to iterate back to considering alternatives and refining the solution. And then finally, you test the solution, which could identify problems that will cause you to iterate back to previous steps. As we're designing solutions to a problem, it is most often critical to break it down into manageable pieces. And when I teach the course that's a prerequisite to this course, I often talk about the first step is input, second step processing, third step output. That is a very rudimentary breakdown of any program you would write. So when we write software, we're going to design pieces that are responsible for certain parts of the solution. And this is often called stepwise refinement or a top-down design. And as we continue to break down parts of the solution into more manageable pieces, we find that an object-oriented approach lends itself to this kind of solution decomposition, breaking problems down into more manageable parts. So we're going to continue to decompose our solutions into pieces, and we will call those objects and classes. Stay tuned. Next, we're discussing development activities. And these can be broken down into four broad categories or broad development activities. The first is of critical importance. Having worked as a programmer where requirements came to me from an industrial engineering team, there was often much clarification needed in establishing the requirements. So that in itself can become an iterative process, because all too often the individuals establishing the requirements are not programmers themselves. The rest would be considered the role of the programmer or programming team in creating a design, implementing the design. Once again, those two steps can be iterative. Okay? Try to implement a design, you may encounter errors or identify efficiencies that weren't considered in the original design, so that can become an iterative loop right there. And obviously testing is the final step before a program goes into a production type mode. Here we have the author's definition of those four stages or development activities. And software requirements are often expressed in what's called a functional specification document, and they specify what a specific program must accomplish. That's glossing over a lot of detail right there. All of the available data and input that are provided to the programmer are clearly delineated in that software requirement or functional specification. Software design indicates how a program accomplishes the requirements, and then implementation is the formal process of coding the solution to solve the problem. And then testing is ensuring that a program will solve the intended problem given all the constraints under which it must perform. And this typically involves some test data, given inputs that yield a known set of outputs, and most likely a driver program or two to test the functionality and accurateness of the program. The purpose of this course is to cover object-oriented programming. And obviously Java is an object-oriented programming language, and the object is the fundamental entity in an OOP, object-oriented programming language, as it is in Java. And objects can represent real-world entities. For instance, an object can represent a particular employee in a company, and each company and the employee, thus the object representing that employee, handles all of the data related to that employee and the processing that takes place with that data. Data might be the attributes of that object, the employee's start date, their title, their age, their wage, all those attributes, and all of the processes that are enacted upon with that data. An object has two main components, state and behaviors. And the state is the descriptive characteristics or the data associated with the object, and the behaviors, what it can do or what can be done to it. And those are typically what we call member functions, which were covered in the prerequisite class, CSC 121. So the example here is the state of a bank account includes its account number and its current balance. The behaviors associated with a bank account include the ability to make deposits and withdrawals, and I'm sure transfers would be in there also. Okay? Note, the behavior of an object might change its state. A deposit will change the current balance. A withdrawal will change the current balance. A transfer will change the current balance of one account, or one, I guess it's one account within, the savings account versus the checking account versus a money market account. Okay. An object exists within a class or is defined by a class. And the class is the prototype, or as the author calls it, the blueprint of an object. And the class uses methods to define the behaviors of the object. So a class that contains the main method of a Java program represents the entire program. Class represents a concept, or an object represents the embodiment of that concept. So, and obviously, well, not obviously, but should be noted that the same class can be used to create multiple objects. Remember, the class is the blueprint and the object is the embodiment of the class. Here's an example. I'm not sure that I love this example, but class is like a blueprint from which you can create many of the same houses with different characteristics. So the class might be the basic house, and different models of the house then become synonymous with objects. Two very important terms are introduced here at the very end of this introductory lecture. An object is encapsulated, and that protects the data that it manages. And please know, we're going to drill down at very significant levels of detail on each of these. So a particular class can be used to create or derive another class via inheritance. In other words, a class can inherit many of the attributes of another class. And if you remember, in C++, we had the IOStream class, and then we had the FStream class library, which contains the IFStream and OFStream class. And they inherited many, many of the attributes of the IOStream class. Classes thus can be organized into hierarchies. And once again, obviously I need you to understand these terms, but we are going to spend a significant amount of time becoming experts in these terms. Here, in our final slide of this audio lecture, we see a graphical depiction of classes and objects and the hierarchy that can exist between classes. So a class such as a bank account defines a concept. And then within that bank account, we can have encapsulated objects are created from the prototype or the blueprint bank account. And it might be John's bank account, Jason's bank account, Mary's bank account. Those are the objects. And they have data associated, characteristics, data associated with them, such as balances and name and address and all those other defining attributes. So classes can also be organized into inheritance hierarchies. So we can have a class called account. And then we can create a class, charge account, that inherits characteristics from account, thus bank account. And from bank account, we could have savings account and checking accounts. These are all classes in a hierarchy that feed up to or feed off of, if you will, the basic or the most high-level account class.